Have you ever wondered how you can tell when a chemical reaction is finished if you can't see it? What if the solution is dark or muddy or completely colorless? You can't use a traditional color-changing indicator. So, how do you find that perfect endpoint? Well, what if instead of watching the reaction, you could listen to it using electricity? Hello, future engineers. Welcome to the channel where we make complex topics simple. Today, we're diving into a powerful technique called conductometric titration. It's a fancy name, but the idea is brilliantly simple. We're going to track a reaction by measuring how well the solution conducts electricity. In this video, you will learn, first, the basic principle of conductometry. Second, how a special device called a conductivity cell works. Third, we'll walk through the most classic example, the titration of a strong acid, HCl, with a strong base, NaOH. And finally, we'll break down exactly why this reaction creates a perfect V-shaped graph. By the end of this video, you'll be able to sketch and explain this titration curve with complete confidence. Let's get started. Formally, conductivity is the measure of a material's ability to conduct an electric current. In solutions, this current is carried by ions. Okay, let's make that simpler. Imagine the solution is a highway and the ions are cars. The electrical current is the flow of traffic. Now, not all cars are the same. Some ions are like super fast sports cars. They zip through the solution carrying a lot of current. Others are like slow, heavy trucks. They move, but not very efficiently. The two fastest sports cars in chemistry are the hydrogen ion, H+, and the hydroxide ion, OH-. They are exceptionally good at carrying current. Most other ions, like sodium, Na+, and chloride, Cl-, are the slow trucks. Conductometry is simply the act of measuring the total traffic flow on this ionic highway. Picture a beaker with two platinum plates, or electrodes. When we apply a voltage, the positive ions move to the negative electrode, and the negative ions move to the positive one. In a solution of hydrochloric acid, we have lots of those H+ sports cars moving very, very quickly. This creates a high traffic flow, or high conductivity. This principle has a very common and important application, measuring the purity of water. Absolutely pure, deionized water has almost no ions in it, no cars on the highway, so its conductivity is extremely low. Even a tiny bit of salt contamination will add ions, and the conductivity meter will immediately detect it. Now, let's put this idea to work in a real titration. We're going to slowly add a strong base, sodium hydroxide, or NaOH, to a beaker of a strong acid, hydrochloric acid, or HCl. The chemical reaction happening is a simple neutralization. An acid and a base react to form salt and water. Let's go back to our highway analogy. Initially, our beaker is full of HCl. This means we have a lot of fast H+ sports cars and some slower Cl- trucks. The overall traffic flow or conductivity is very high. Now, we start adding NaOH from a burette. The NaOH contains Na+ ions, slow trucks, and OH- ions, fast sports cars. But here's the crucial part. As soon as an OH- ion enters the beaker, it finds an H+ ion and they react to form water, H2O, which doesn't conduct electricity. So for every drop of NaOH we add, we do two things. One, we remove a super fast H+ sports car. And two, we replace it with a slow-moving Na+ truck. Think about that. We are trading a sports car for a truck. what happens to the overall traffic flow? It goes down. The conductivity starts to drop sharply. This continues until we reach the equivalence point. This is the exact moment when we've added just enough NaOH to neutralize every single H+ ion. All the sports cars are gone. The highway is now filled with only the slow trucks, Na+ and Cl-. This is the point of minimum traffic flow, or minimum conductivity. Now, what happens if we add just one more drop of NaOH? There are no H+ ions left to react with. So the fast OH- sports cars from the NaOH now start to build up in the solution. We are now adding sports cars back onto the highway. And so the traffic flow, or conductivity, starts to rapidly increase. This whole process, a sharp decrease, a minimum point, and a sharp increase, creates a beautiful V-shaped curve. On the y-axis, we plot conductivity. On the x-axis, we plot the volume of NaOH we've added. As we add NaOH, the line goes down, down, down. This is the region where H+ is being replaced by Na+. Then it hits a sharp minimum. That's our equivalence point. After that point, as we add excess NaOH, the line goes up, up, up. This is the region where we are adding excess, fast-moving OH- ions. The reason this works so well is clear when you look at the numbers. The ionic conductivity of H+ is almost 7 times that of Na+, and OH- is nearly 4 times faster than Na+. It's this huge difference in speed that gives us such a sharp and obvious V shape. This method is fantastic for situations where normal indicators fail. Imagine you're analyzing a sample of dark-colored vinegar or a murky wastewater sample. You'd never be able to see a color change. But a conductivity probe doesn't care about color. It only cares about ions, making it incredibly versatile for these challenging samples. All right, let's solidify this with a quick example you might see on an exam. Problem: sketch and explain the conductometric titration curve for 100 milliliters of 0.1 molar HCl against 0.1 molar NaOH. Solution: let's break it down into 4 stages. Stage 1, the initial point. Before we add any NaOH, the solution contains HCl, which means we have highly mobile H+ ions and Cl- ions. The conductivity starts high. Stage 2, before the equivalence point. As we add NaOH from 0 up to 100 milliliters, the fast H+ ions are replaced by the slow Na+ ions. This causes a sharp linear decrease in conductivity. Stage 3. At the equivalence point. At exactly 100 milliliters of NaOH, all the H+ ions have been neutralized. The solution now contains only sodium chloride, or NaCl. This is the point of minimum conductivity. Stage 4. After the equivalence point. As we add more than 100 milliliters of NaOH, we introduce excess, highly mobile OH- ions into the solution. This causes a sharp linear increase in conductivity. The graph. When you plot this, you get that perfect V-shaped curve. The equivalence point isn't a single data point you measure, but rather the intersection you find by drawing a straight line through the first set of points and another straight line through the second set. The point where they cross is your answer, 100 milliliters. It's clean, simple, and very accurate. So let's recap what we've learned. 1. Electrical current in solutions is carried by ions, and some ions, like H+ and OH-, are much, much better at it than others. 2. In a strong acid, strong base titration, we start by replacing a fast ion with a slow one, causing conductivity to drop. 3. After the equivalence point, we start adding a different fast ion, causing conductivity to rise again. And 4. This drop and rise create a sharp V-shaped curve, allowing us to find the equivalence point with high precision, even in solutions where visual indicators are useless. And that's conductometric titration in a nutshell. It's a powerful tool that turns a chemical reaction into a simple, easy-to-read graph. If this explanation helped you, please give this video a thumbs up and subscribe to the channel for more engineering content made simple. Do you have any questions or want to see another type of titration explained? Let me know in the comments below. Thanks for watching, and I'll see you in the next video.